All right, let's see. I hope this is it. Right, good afternoon, everyone. Thank you so much. This is my second time at NANOG, so I appreciate the opportunity to present to all of you. I'm with Finisar Corporation. Some of you may be familiar with the company. We're the largest manufacturer of optical transceivers around the world. 14,000 employees. We sell to mainly to system OEMs, but also to end users such as yourselves. And today, I'm going to talk about different topic to what I normally do, which is typically talk about optics, transceivers, and data center, and so on. Today, I'm going to talk about specific issues that were found and solved in the open networking ecosystem with working with optical transceivers. Specifically, what are some of the benefits for innovation, but also challenges for interoperability that open networking brings into our space, and how something called open optical monitoring that we spearheaded, but it's an open effort that we did within OCP, helped solve this problem. Then I'm going to show you some application examples, how you can use it, how you can access it and use it, and some of the latest news for those of you that are already using it. So let's first explain what the problem is, and some of the basics, and I know all of you understand this. Traditional networking ecosystem works. The system OEM, such as Cisco, Arista, or Dell, whoever it is, typically take care of a whole stack in a switch, all the way from procuring the optical transceivers, even though that you can procure separately, given that they're pluggable. But they give you the cell, the switch, they integrate the IC, the network IC, the network OS, the applications, they're all part of the same package, fully vertically integrated that a system OEM gives you. So that means that all the integration with the optics, which means the status and control information for the optical transceivers, is all taken care of by the system OEM software. However, that changes when you go into an open networking ecosystem where disaggregation brings a lot of innovation and cost advantages. It brings also another set of complexities and challenges. So as you very well know, in the disaggregated model in open networking, you have separate vendors for the optics, separate vendors for the white box, for the silicon IC, for the switching IC, that is, also for the NOS, and of course for all the applications. There could be hundreds of applications that are available out there that have to make use of this fully now disaggregated model. So things like standardization, interoperability among all these different elements in the ecosystem, open APIs come into play. Innovation is also one of the benefits, but again, if we take care of standardization, interoperability, and open APIs. And of course, the bottom three at the base of this is, as always, quality, reliability, and assurance of supply. You want something that's reliable, that works, and that is also available from multiple vendors or multiple sources. So let's talk about standardization for a minute, which open networking actually even make it more relevant. There are many standards out there for different things. You have IEEE and things like T11 standardizing optical and electrical interfaces, Ethernet, fiber channel, OIF, internetworking, telecom interfaces. There's also the MSAs that govern transceiver form factors, things like SFF, CFP, QSFP-DD now for 400G. OSFP, there are many different MSAs that govern the mechanics and the electrical, in some cases, of the transceiver form factors. And then you have some of the MSAs like CWDM4 and others that specify some optical applications for specific needs. So all of the standards actually are becoming even more relevant to make sure that transceivers talk to each other and that different transceivers from different sources work also in different white boxes. So let's do a brief aside and show what the state of the industry is in data centers in particular, and this is trying to encompass all kinds of data centers. Today, 10G in the rack is still being deployed to the server in the vast majority of data centers still out there. However, 25G has already started to be deployed, specifically in big hyperscale data centers, big clouds, but also other large enterprise, for example. And 50G and 100G, next generation 100G, that's going to be the next interface for servers. And that standardization has already begun, is ongoing actually within the IEEE. And you can expect a combination of both 50G and 100G in next generation servers. Again, first coming from the leading edge, which is always the large clouds, the large public cloud hyperscale data centers. Between data center racks or switch to switch, 40G is still pretty much being deployed in many data centers. However, 100G, as the previous speaker said, is massively being deployed now by the big clouds, 100G QSFP28s, multi-mode, single-mode, all kinds of different interfaces are being out there being deployed. And next generation speeds are already standardized. And actually, at 200G and 400G, the IEEE BS task group standardized, or ratified rather, 802.3 ratified 400G standard a couple of weeks ago in Geneva. And they're now starting to work on next generation 400G interfaces. Low number of fibers, low number of wavelengths, and so on for next generation 400G after initial deployments. So again, I'm not going to talk in detail about that effort today. It's a topic that I really like. So if any of you want to talk about it, please see me after the talk, and we can surely discuss. Then between data centers, DCI or anywhere in the WAN, believe it or not, 10G tunable still pretty much being deployed all over the world. However, the leading edge has been using 100G now, client interfaces so far, but also now coherent interfaces, coherent ACO or DCO, 100G, 200G for DCI applications. And next generation is going to be, of course, higher speed. So 400G is being standardized by OIF for next generation data center interconnects. And optic vendors like us are looking beyond that. We're looking at 600G, even things beyond that for the next generation of DCI deployments. So again, the summary is standardization both in the optical interface side and the transceiver side will continue to be very important in an open networking environment, and it's important to give users the tools to identify the performance and make sure the performance of the transceivers meet those standards. So interoperability is a big word, of course, in the open networking space. The group that has been key in doing this is Open Compute, where a large combination of NOS and switch cables, transceiver modules are continuously being tested for performance. The proven solutions are added at an open networking integrators list that's widely available. And that testing occurs within the interoperability lab at the University of New Hampshire. That test is ongoing, it happens weekly. However, there are a couple of plug fests that happen maybe once or twice a year. The last one was in May 2017. The focus there was 100G CWDM interoperability, but there are many different interfaces continuously being added. If you go to their website, you're going to see the list of combination of switch vendors, NOS, optics, and copper cables, all these different configurations that have been tested. So we, of course, participate in those efforts, and it was actually there that the issue I'm going to talk about was identified originally, like 3 years ago. So the issue with optical transceivers is that all this flexibility that open networking provides was having an effect on the type, on how users could access the information inside the transceiver. And that information is both static and dynamic. Static information, something called serial ID, that gives you information about the module itself, the vendor, the interface type, which standard it meets, serial number, manufacturing code, and all kinds of static information the transceiver has. There's also dynamic information about the link, transmitter and receive optical power, voltage, temperature, and so on, which is important to gauge the performance of the link. All that information is typically read and reported by a system OEM. But again, it was getting lost now in the open networking ecosystem. There was no consistent way for the applications, for the end users ultimately, to access that in a standardized fashion. So it really depended on your combination of switch IC and which switch vendor, which white box vendor, and so on, and the NOS also. So again, each switch, each NOS had a different way of accessing that data. So that was really a problem early on. So ideally, what you want is something that provides, or a driver initially, basically, that provides a standardized way to access all that data regardless of the particular implementation of your switch. And that's actually what we set out to fix in something we call open optical monitoring that I'm going to discuss in the next few slides. So open optical monitoring is an OCP project. We identified that issue and we started a project back in 2015. The sponsors, Finisar was one of them. As you can see, some of the other names are the big names in open networking. And the aim was to create a decoding layer, some kind of library that decodes the low level, if you will, data being read via I2C to the transceivers interface into the transceiver module, and converting that into a northbound interface. So it was an open API that could be read in, could be queried in Python. So we kicked off that in 2015. What it is we're now done with that, although improvement is continuous. It's basically a Python package that provides, as I said, a standard API that reads and writes to optical transceivers. That EEPROM information inside the transceivers is actually encoded or decoded in key value pairs, and it can be queried, as I said, obviously in Python. It's the same API for any Linux-based NOS. So any switch, any transceiver type, any transceiver vendor, as long as they meet the standards in the MSAs, via OOM, that transceiver can be queried or controlled in many cases. It's obviously open source, very easy to maintain and to extend. Now here's an example of a few lines of code. I have more applications examples coming up, but that's basically what that could, what you need to write to get in this case, all the status information of all the ports in the switch. So some high-level block diagram of how it works is essentially, we provided actually both a decode library, a decode library called the OOM decode library that's already out there, and also most recently a universal optics driver that can provide a multi-access actually to the I2C interface for a multiplicity of switch and white box combinations, and I have some information on that coming up. So a few technical details, and again, I'm an optics guy, so I have to trust our software guys who gave me this slide. So the decode library is table-driven. Each key has a location and a decode function for that key value pair. There is also certain decode functions for specific data formats. We do all that as part of the OOM library. For example, the temperature information of the transceiver is encoded in a 16-bit 2's complement value in units of 1/256 degrees. That's just the way that the MSA defined it in EEPROM, and all that conversion is done to just degrees by that library. It also includes collections of keys, so you can query groups of parameters at the same time. So things like serial ID or DOM actually returned a set of optical performance information for that port. The driver that we've actually contributed most recently is a standard Linux kernel driver, and it can support any transceiver, standard transceiver, SFP, or QSFP. And again, it accesses the EEPROM using the Linux I2C APIs that already exist out there. And it's a very universal driver and actually a little bit more comprehensive than some of the others that the white box manufacturers have provided. And again, this is now part of the OCP project, OOM. Some examples of how you would access information on the port. So the first bullet point there gets a list of all the ports in a switch. After you call, of course, that OOM library. The second example, the second bullet point, you get a specific parameter, a specific value for a specific parameter you're looking for. Or alternatively, as shown in line number 3, you could get a collection of parameters by invoking, in this case, the DOM function. As you can see on the example on the right, so those 3 simple lines will get you all the info. And again, if you had 32 ports, you will get 32 lines of all the optical information on that particular box. You can also run it over the network. There are some implementations that using JSON, you can actually run it over the WAN. So for things like remote monitoring or remote maintenance of your network, this can actually be also queried over the network. So what is this good for? What applications? Well, the applications are very similar to what people use today in the standard system OEM paradigm. So you could do things like inventory, where you track and you verify the transceiver types, what you think you have versus what you really have, the optical interface in those transceivers, serial numbers, manufacturing date code, and so on for warranty purposes. You can do health monitoring. You can read, as I showed before, information on the TX and RX optical power. You can track that in real time, so you can see trends. If that optical power is coming up or down. It could indicate that a port is dirty, for example. Temperature, alarm and warning thresholds can also be monitored to make sure that they are adequately configured for those boxes where you can actually configure those thresholds. Diagnostics, this means actually network diagnostics. So there are ways that you could actually change the DOM information and also those alarm and warning thresholds to segment performance across your network. And you can see things like, if a fiber link, for example, is getting too close to the maximum edge, right? If the link budget is getting too close to what the fiber link can support. So you can do some proactive maintenance and diagnostics of your network. And then custom uses, and this is where innovation comes into play. There is different transceiver vendors like ourselves or others can actually provide innovative new features in those transceivers. Before, in the traditional paradigm, you have to go through a system OEM. They'll take 2 years to qualify the feature. They try to get a second source for the feature and so on, which is great because they make sure that thing works very solidly, but it takes a long time. So innovation can now happen much more rapidly. We can get to the end user right away in an open networking model, and we can allow you to control or get status of that new feature by using the standard EEPROM in the transceiver, and you can read that via Python. You can create your own applications from day one with an open API. So again, some examples of what all of this look like. This is an example of an inventory where this only shows 5 of the parameters, but there are actually literally tens of parameters of static information, also called serial ID, that you can get from a transceiver. And this again is what the Python code would look like. Very straightforward to get a list of ports. Similarly for health monitoring, and this is a simple GUI we created where we show in this case 4 of the parameters and the alarm and warning thresholds, but you can create your own applications obviously to display all the metrics of that optical link. Again, very easy to get a list of all those parameters for all the ports in the switch. Diagnostic, very similarly, I can talk about in detail about some of this offline if you like, about some of the implementations some of our customers have done. In this case, you need vendor tech support, which means optical vendor tech support to change things in the transceiver to allow this segmentation of performance and be able to more diagnose network performance at the network level, not just at the transceiver level. And then, as I mentioned, the custom uses is an example where, for example, through Python, you can actually light up the pull tab in a transceiver, to identify a specific transceiver out there in the field. You can actually, via I2C, which again is done via Python now, you can actually say, transceiver import 2 of switch number 3, please start blinking. So somebody on the floor can actually remove it. So this is a kind of innovative new feature that can be implemented very rapidly and brought to market very rapidly and implemented using OOM. We've shown this a couple of times already at the OCP summits back in 2016 and 17. Again, some of these applications are shown that I mentioned, are shown in the GUI there, and I can talk about this in detail to anyone who's interested. And then how can you access it? If you're interested in playing with it, it's all open and free, of course. It's part of OCP. You can go to the OCP GitHub. The code is there. You can download it, use it, improve it. Please share your use cases with us in the project. It is being done in interoperability testing within the University of New Hampshire, as I mentioned, and it has been demonstrated with multiple combinations of switches, NOS, and so on and so forth. There are about 200 keys already decoded for all types of transceivers that you can see there, including more recently some CFP support, which is still being used in routers primarily, not so much in switches. So some of the latest OOM news, for those of you that have been tracking this, are part of OCP maybe. In the last year, we've introduced a universal Python shim. This was to solve a specific issue where it was needed to compile C code to install OOM. That's no longer required. We then introduced CFP family support. Again, for those of you using this in routers, CFP, CFP2, CFP4 family was important support as well. The universal Opto-E driver was released. And again, this can be used on any Linux-based NOS. It actually, we believe, is better than some of the existing drivers out there, which are more white box specific. This actually has better functionality, more transceiver capabilities, EEPROM capabilities. And then most recently, Opto-OE, that driver is now part of a couple of distributions. ONL distribution is being used in 8 Acton switches and 1 Quanta switch. It's also in the Sonic distribution, being used by 2 Acton switches and 1 Inventec switch. So that's fresh off the press, actually, from a couple of weeks ago. So again, a large amount of interest in OOM, in this part of the open networking community. So feel free to, for those of you that are interested and it's relevant, go to the GitHub site, play with it, send us your feedback, ways we can improve it, or just improve it yourself and can contribute to the project. That's what I had. I'd like to actually, the real expert in this at Finisar is Don Bollinger. Those of you attending the OCP Summit next month, you will see Don, he's part of he's actually leading a panel. He also has a short presentation with more in-depth, specific technical information on some of the latest improvements in OOM at the OCP Summit in San Jose coming up in March. So that's the end of my talk. Any questions? All right. If there are no questions, I'm available to talk about any optical issues and topics. That's really my passion, so please find me in the hallway. If not, other than that, thank you so much. Appreciate the time again and the opportunity.